Hello everyone. In this lecture, we will continue our discussion of IP addressing. We're going to talk about how to obtain and configure an IP address. An IP address can be hard-coded by the system admin or a user in a file. This is termed a static IP address. In a Windows-based operating system, for example, you can open the control panel and in the network configuration go to TCP IP properties and set the IP address. In Unix, the entry can be made in the /etc/rc.config file. But the IP address can also be assigned automatically using a protocol called DHCP, which is the Dynamic Host Configuration Protocol. Most of you are probably very familiar with this. Let's look at the details about DHCP. The goal of DHCP is to provide a host with an IP address dynamically from a network server, which is called the DHCP server. This happens whenever that host joins the network. DHCP automatically assigns and keeps track of IP addresses and any subnetworks that require them. Nearly all IP addresses are dynamic as opposed to the static IP addresses that never change. One of the features of DHCP is that it provides IP addresses that expire. When a DHCP server assigns an IP address, it leases that address to the host for a specific amount of time. Once the lease time expires, this IP address can be used for some other host when it enters the network. Note that the server can also make a DHCP reservation, so a host will always have the same IP address. DHCP is a very robust way of administering IP addresses, especially for mobile users, since they only need IP addresses on a network for a very short time. So how does DHCP work? Let's look at the example on this slide. A laptop, which is the DHCP client, is entering the network, which includes the DHCP server. This laptop needs an IP address. We see there are 3 subnets in this network, and the laptop is entering the subnet, which has a network address of 223.1.2.0/24. Note that the DHCP server is on the same subnet. Now, if a host is in the other 2 networks, 223.1.1.0 and 223.1.3.0, request an address from a DHCP server, there will have to be a relay agent to send the DHCP messages across the router to the network that the DHCP server resides in. Typically, the router can be configured to act as the DHCP relay. How does this DHCP client-server interaction work? The host that wants an IP address broadcasts a DHCP discover message. The host is a DHCP client in this conversation. The packet is a broadcast packet with a destination IP address of all 255s because the laptop does not know the address of the DHCP server. The source IP address is all zeros because the laptop does not yet have an IP address. The DHCP server or servers, there could be more than one, hears this broadcast and looks for an available IP address to hand out. This available IP address will be in a defined pool of IP addresses, and of course, will not be an IP address that's already in use. Then the server responds with the DHCP offer message containing the transaction ID of the received discover message, the proposed IP address, and other configuration parameters. For example, the server could offer the address of 223.1.2.199, which is on the same subnet as the DHCP server. This offer message is broadcast to all nodes on the subnet using the broadcast address of all 255s. The laptop does still not yet have its IP address. Since more than one DHCP server can be present on the subnet, The host may be able to choose from among several offers. The host responds to its selected offer with a DHCP request message echoing back the configuration parameters. The DHCP server answers back with a DHCP ACK message confirming the assignment of the IP address and providing additional configuration parameters to the host. The DHCP server updates its address database and updates any other DHCP servers. Once the client receives the DHCP ACK message, the interaction is complete and the client can use the DHCP assigned IP address for the duration of the lease. The DHCP server can provide more than IP addresses. This configuration information includes the IP address of the first hop router, which is also called the default gateway, the name and address of the DNS servers, the network mask, the lease time, and the DHCP server. The DHCP server can also provide optional information, which can include such items as the IP addresses of time servers and log servers. Let's look at this client-server scenario from a TCP/IP protocol stack standpoint. The connecting laptop needs an IP address, as well as the addresses of its first hop router and a DNS server. Notice that DHCP sits at the application layer. The laptop, upon arriving at the network, will send its DHCP discover message encapsulated in UDP as its transport layer, using port 68 as its source port and port 67 as the destination port. The UDP segment is encapsulated in IP. The IP packet is encapsulated in a data link frame, which is an Ethernet frame in this example. This Ethernet frame is a broadcast using the destination address of all Fs. The DHCP Discover broadcast is received at the DHCP server running on the router in this example. The DHCP server demultiplexes the message at different layers and determines that the laptop is requesting this configuration. This same process of encapsulation and de-encapsulation occurs at each of the other messages in the DHCP client-server conversation. Let's look at a partial Wireshark capture of a DHCP exchange. What we are seeing is the decode of the DHCP application itself. The first line of the left-hand side indicates that the message type is a boot request. This is a legacy because DHCP is a successor to the BootP protocol. If we look down the left-hand side to option T = 53, we will see the type of boot request is actually the DHCP reply, which is the host client's response to the DHCP offer from the DHCP server. So we are not looking at the entire DHCP process on this slide. Option T = 50 is the host's requested IP address. At this point, the host's IP address is still listed as all zeros because the DHCP server has not yet confirmed the address assignment. Also, we can see that the host has requested additional information under option 55, parameter request list, including subnet mask router, which is the default gateway, domain name, DNS server, and an additional item, NetBIOS over TCP/IP name server. The right-hand side of the slide is the DHCP server's ACK response. The DHCP server has responded to all the host's requests for additional information except for the NetBIOS over TCP/IP name server. We have talked about how individual hosts get their IP addresses. Now let's look at the higher level picture. ISPs are allocated blocks of IP numbers. ISP assign portions of their blocks to individual organizations or individuals for home access. Organizations are assigned these subnets based upon the number of host IP numbers required. Let's examine the numbers shown on this slide. This ISP has a block of IP addresses designated by 220.3.16.0/20. Recall from the previous video that for this block, the first 20 bits define the network. The remaining 12 bits are reserved for the host. A subnet this size could contain as many as 4,094 unique host addresses. That's 2 to the 12th minus 2. This subnet could also be further divided into more subnets, which have addresses for fewer hosts. As we see from the slide, each of the organizations have been assigned subnets with 23 bits for the network and 9 bits for the host. These organizations each have enough addresses for 510 hosts. That's 2 to the 9th minus 2. By aggregating individual organizations' subnets, which are contiguous, the ISPs advertise routes more efficiently. Instead of advertising individual routes for each of the 8 organizations, the ISP can advertise just one route. Even though routes can be aggregated, more specific routes can still be used. In the diagram, notice that ISP's RS is advertising Organization 1's address block, when that block is part of a larger block advertised by fly-by-night ISP. In general, the more specific route, the one with the longest matching prefix, will be chosen. Now, how does an ISP get a block of addresses to assign to individual organizations? The global address space is managed by the Internet Assigned Number Authority, IANA. IANA allocates blocks of addresses to regional Internet registries, RIRs. The ISPs request their address blocks from the RIRs. The Internet Corporation for Assigned Names and Numbers, ICANN, based on a Memorandum of Understanding, is the institute which currently performs IANA operational functions. That is responsible for the central registration of domain names, IP addresses, and ports. This final slide shows the geographical areas of responsibility for the regional Internet registries. Next up, we will discuss network address translation.